Good morning everyone. Today we will discuss generalized impedance converter. Okay. Operational amplifier have many applications. One of its application is this generalized impedance converter. Good morning everyone. Good morning. Good morning Vikas. Impedance conversion is required in many applications where there is impedance matching like of things, or you want to create an ideal current source, or you want to create an ideal voltage source. In such situations there is a need of impedance conversion. For a voltage source there is a resistance or impedance in series with the voltage source that comes naturally. So this impedance is a small impedance though, but it comes in series with the load. If load is also small, then it is a very big problem. Therefore impedance matching is required. Other thing is also similar to this voltage source, there is problem in the current source also, so for that also impedance matching is required. Okay, so the discussion is here that how to convert impedance, or means what we mean by the impedance conversion. That is what need to be discussed in this lecture. That in impedance converter, what is expected, that what should be the, so converters are many, and converters we have already discussed some of the converters like voltage to current converter, and current to voltage converter. Another subjects you might have studied AC to DC converter, and there are many one energy to one form of energy, one form energy to other form of energy. Sometimes we convert mechanical energy into electrical energy, or electrical to mechanical. So there are many converters, and converters are also very useful. And today I am talking about a impedance converter. So before going to impedance converter, we should also discuss little bit about the impedance. Impedance is something which is there can be a combination of resistance or impedance. So this can be R plus J times XC. This can be XL, like this. It can be R plus 1 upon J omega C, means this is a capacitive kind of impedance. This can be Z. This is generally represented by Z. So Z equal to R plus J omega L. Or this can also be equal to R. This impedance can be equal to only J omega L. Impedance can be equal to only Z equal to can be 1 upon J omega C only. So this can be only resistive, can be only inductive, can be only capacitive. This can have a resistive or capacitive combination. This can have resistive inductive combination. This kind of impedances are possible. Okay. And also sometimes it is called that if you are converting a low resistance to high resistance, that is also impedance. Low impedance to high impedance conversion, high impedance to low impedance, that is also a possibility that you are converting from high to low. Sorry for interruption, there was some problem. Okay, so this way these are the conversions that are possible. Okay, so impedance conversion. Okay, then how OPAMP plays a role? What is the importance of OPAMP in this case? So I'll come to the operational amplifier based impedance conversion. Why this come into the picture and what was the need of this? So before going to the generalized impedance converter, I want to discuss about a negative resistance conversion. Means there is one more conversion possible, that is called negative resistance, means positive resistance to negative resistance conversion. So before going to the generalized conversion, I will discuss this one. So we all know we know that we know V is equal to IR. What is this? This is a, what is this equation? This is very famous Ohm's law, isn't it? Very good. Ohm's law. So most of the devices in circuits follow Ohm's law. That means if I increase the current, when current increases, then voltage also increases. Okay. And but by negative, when that means the resistance is positive. This is positive resistance. But if just opposite happens in some device, then that means if there is a like relation like this, that is a negative of Ohm's law, that means when current increases, the voltage decreases, and that is a magical device, and that means the negative that negative resistance. ये कैसे संभव है? मीन्स ये हो कैसे सकता है कि आप करंट बढ़ाओगे वोल्टेज कम हो जाए? ऐसा बहुत मुश्किल है. ऐसा कैसे कौन सा डिवाइस हो सकता है? क्या लैब में या किसी सिमुलेशन में या किसी सर्किट से हम लोग ऐसा कैसे बना सकते हैं क्या कि आप वोल्टेज बढ़ाओगे और करंट कम होना चाहिए? Have you studied in any other subject or any other topic this kind of thing, that when voltage increases, current decreases? Any answer? No. Okay, if anyone have studied in electronic devices, that there is a tunnel diode. In tunnel diode, if there is a characteristics like this, that this is voltage Vi characteristics. So for a simple diode, the characteristics is like this, and this resistance in all ways will be a positive resistance, because current is increasing when voltage is increasing. But in tunnel diode there is characteristics like this. When you are increasing voltage, then it will go up, and after some time it starts decreasing like this. So this in this situation, the resistance becomes negative, because we are increasing the voltage but current is reducing. So here the resistance is negative. We have made that means there are some devices also. This is a tunnel diode. If you have not studied about it, you can study. This is means important for the competition exams and the other exams also, that you should know about the tunnel diode. This is a normal diode. This is a normal. This the characteristic that I was drawing previously. This characteristics is for a normal diode, and this characteristics is for the tunnel diode. So tunnel diode is showing the negative resistance. So what is the advantage? Means what advantage means is for the negative resistance? As I told that negative resistance का फ़ायदा क्या होगा? क्वेश्चन ये है कि हम क्यों ऐसा, मतलब हम नेगेटिव रेजिस्टेंस के बारे में बात कर रहे हैं. मैं इसलिए बात कर रहा हूँ क्योंकि जो वोल्टेज सोर्सेस होते हैं, जो प्रैक्टिकल वोल्टेज सोर्स होता है, मान लो उसका वोल्टेज V है, तो उसका जो एक सीरीज में रेजिस्टेंस RS होता है. अगर आपने लोड यहाँ पे RL लगाया, तो जो सर्किट का इक्विवेलेंट लोड है वो RS प्लस RL होगा. That means this voltage source is not ideal source. It have some positive resistance in series with that. So if I could have some resistance, if I generate some resistance minus RS in series and connect it in minus RS and connect it in series with it, and then connect load, तो अब क्या होगा कि इक्विवेलेंट रेजिस्टेंस होगा वो RL ही रहेगा, क्योंकि यहाँ पे RS और माइनस RS दो एक आपस में एक दूसरे को कैंसिल कर देंगे. सो दिस नेगेटिव रेजिस्टेंस विल मेक दिस सोर्स टू बी आइडियल. If somehow I could generate a negative resistance, then this can make my voltage source ideal source. This was a source already there, and I have connected this negative source in series with that. And this way, this can be helpful for making the ideal voltage sources. Similar to this, I can also do for the current source, that I can connect the current source in parallel to the previous one. वहाँ रख दो. अभी नहीं, अभी क्लास की बात करेंगे. Okay. So ये similar to this, I can also do for the current sources. In current source there is a source resistance in parallel to this. So minus RS, if I can connect in parallel to this, so RS and minus RS will cancel to each other, and it will show infinite resistance. Means this minus RS and RS, you can see the R parallel will be equal to RS into R minus RS divided by RS plus minus RS. So this will result in the infinite impedance, and this source will become ideal source. I is now ideal. This is a very great advantage, that we could generate ideal sources with the help of negative resistance. Okay, so this how this negative resistance can be generated using OPAMP. Let me draw a circuit for this. So I am drawing a circuit for OPAMP, and let us analyze the circuit with this. So if I have voltage input here, some voltage input I am applying, and this input is going to with the in a op-amp minus plus, and here is a resistance R1, and here is a resistance R2, and there is one more resistance R3. Just visible to you all? आप सबको ये सर्किट दिख रहा है? फटाफट 2 मिनट में सॉल्व करके दिखाइए, फटाफट जल्दी जल्दी इसमें आंसर बताइए कि मुझे इसमें मैं कुछ करता हूँ। तो हमें पता है कि बाई अपना मेथड क्या है, बाई वर्चुअल ग्राउंड कॉन्सेप्ट, वर्चुअल ग्राउंड concept. What can I say that this voltage at this node E, I write it N, I write it P. So voltage at node N will be equal to voltage at node P. This voltage is also equal to voltage at node P, and this voltage is also equal to voltage at node N. So as Vn is connected directly to the input, so Vn is Vn, therefore Vp is also equal to Vn होगा. Now the current flowing through this will be equal to, if I take the current flowing through this equal to current, यहाँ से यहाँ तक कितना करंट आएगा. सो करंट अगर मैं यहाँ से ऐसा, यहाँ तो करंट जीरो है, तो जो करंट होगा वो इधर से आएगा. लेट इट बी I1. सो I1 विल बी इक्वल टू Vn minus let this be V0 upon R1. This is equation number 1, and this current will be equal to, this current is I2 suppose, and this I2 will flow also from here because this there is no current going into the op-amp is ideal. So I2 is equal to V0 minus Vp upon R2, equation number 2, and I2 is also equal to Vp minus 0, this is 0, upon R3. Okay, so let us solve these three equations now I have. And find out the relation between Vn and I1. Okay, so I will substitute I2 from here to here. This is equation number 3. आप साथ में नोट करते जाइए अपने नोटबुक में. इक्वेशन नंबर 3. सो from 3 substitute I2. So this will be Vp upon R3 is equal to V0 upon R2 minus Vp upon R2. So V0 equal upon R2 equal to Vp upon R3 plus Vp upon R2, और V0 इक्वल टू लिख सकते हैं Vp R2 by R3 plus Vp. Substituting this value into equation 1, this is equation number 4. So substitute V0 from 4 to 1. This will make I1 equal to V in upon R1 minus V0, so minus Vp R2 upon R3 minus Vp. Let's solve this. I don't know whether I made some Vn upon R1. Just solve this equation. Just solving these three equations. I don't know whether this is to be done or not. Solve these three equations and I got Vn upon R3 equal to minus of I1. ये आंसर आ रहा है कि नहीं आ रहा है, ये वेरीफाई करके बताओ. Happening in this circuit, the current is I have assumed like current is flowing inside this. Instead of going to the ground, the current I1, overall current I1 is coming out of the ground and showing the equivalent resistance of R3. This circuit is showing equivalent resistance of R3 and the current is going into the circuit, into the input. This can be understood from this circuit. So the negative resistance is very good device that have just that have practical applications in the power supplies and many basic circuits. All power sources including voltage and current regulated power supply have some internal resistance. So the simplest case, the chemical batteries which are usually have few ohms of resistance and in series with the battery. So we can find out the exact value of the series resistance of source resistance of the battery by doing some lab test or some circuit test. Then design a negative resistance converter in series with the battery, and that will cancel out the positive resistance with the negative resistance, and the end result will be a combined circuit that will act much closer to an ideal voltage source without changing its output. And it will not depend on the load. So that is how we can make an ideal power source using the negative resistance. But we need a fine-tuned power source, and it should not change its load, its series resistance. Okay, so yes, in this, in addition to this, we can do more also in this circuit, and someone may think that if I change the instead of resistance, if I make a capacitance into this, means instead of R3, instead of a resistance R3, if I connect a capacitance, that will improve a lot of things in this circuit, because a negative capacitance becomes an inductor. And that is a great achievement. That will be a great achievement if you could design an inductor using a capacitor. Okay, so you said as I told that this the impedance of an inductor is j omega L, the impedance of a capacitor is 1 upon j omega C, and if I multiply if I say this is a constant, actually omega L is a constant, so j into some constant k, and this is 1 upon j into some constant k. You can say this is k1, this can be k2. If I multiply j in the numerator and denominator both, then this will become minus j upon 1 upon k3 minus j upon k2. Okay, so this is again a constant, and this can be seen this minus j into k3, and this is which is again some minus of ZL can be said, because this is a constant, this is also constant, can be k1 or k3, doesn't matter. So I can say that ZC is approximately ZC equal to minus of ZL. This is a relation that between the capacitive and inductive. So if I can make a capacitive impedance, then I can easily make an inductive impedance. So I can design an inductor. I think you are able, you may be able to understand this thing, this discussion, that what I am saying, that the impedance of an inductor is j omega L. This can be j of some constant, and impedance of a capacitance is 1 upon j omega c, j into 1 upon some constant. If I multiply j to numerator and denominator, this becomes minus j of k3. Therefore, I can say that z is equal to minus j of L, and therefore the impedance of an inductor is negative of impedance of a capacitor. Okay. So what idea is that if I in the circuit that was being discussed in the previous case, if I connect a capacitance instead of a resistance R3, all elements remains. If I connect a capacitance here was resistance R3. If I connect a capacitance instead of R3, and other R2 and R1, these R2 and R1 resistances remain same, because resistance is easier to do design in the integrated circuits. And you should also know that the most difficult thing or most difficult component to design in integrated circuit is an inductor. Why? Because inductor is first of all, it is a bulky. When you design it into the integrated circuit, it takes a lot of area, and other thing is that coils of inductor create electromagnetic radiations and electromagnetic interference in between their rounds. So that is that is why inductances are avoided. That we try that there should not be inductance in the circuit. Means but sometimes it is these inductors are also designed into the chip, but designer tries to convert inductance into the capacitance using this circuit. So but it will work like inductor. This circuit will work like inductor. So this is an equivalent inductor. There will be an equivalent inductor to this circuit, because it will show you that a negative impedance of a capacitor. This will be this will result in Vn equal to xc minus of xc into I whatever I1, like this. If you solve this using the same process that we did in the previous circuit, you will get a relation like this: I1 into R3. This was so I1 into R3 is xc in this case. So this will result like this. So minus xc is nothing but an inductor. So this is an inductor. This is another application of our NRC circuit, means negative resistance circuit, to design an inductor. This is also planned in a separate class, that how to design an inductor. So because inductors are big and bulky and can cause electromagnetic interference in the elsewhere in the circuit, so by using the negative impedance converter, we make a device that works like inductor, and we can eliminate those nasty inductance in designs in the circuit. Of course, there is a problem in this also. There is some problems that you can always will not be able to define a proper value of inductor. So you have to compromise with some values of capacitances available that could be designed. So in practical designs, there are some problems in this, but I can say that this is effective. Now the next thing is that how to next discussion is about the generalized impedance converter. Let us come to that point. So I'll let us design the circuit. The circuit for this is you give input from this point, and there is impedance Z1, and there is another impedance Z2, another impedance is Z3, and another impedance Z4. These four impedances are connected like this. First op-amp is connected between Z1 and there is one more actually, Z5. So this is connected between these two. Input from this point and input from this point goes into the op-amp, and op-amp's output comes like this. This is minus terminal, this is plus terminal. One more op-amp is connected at this point, and at this point, and output of these two goes to Z3, this point. This is the generalized impedance converter. Okay, just see this circuit. This circuit have Z5, 5 impedances and 2 operational amplifiers, and Zi, we need to calculate Zi. Zi means equivalent input impedance, and equivalent input impedance will be equal to Zi can be calculated at this point. So Zi Vi upon the current input, that is to be calculated. You can use our previous knowledge of virtual ground concept and KCL. When you apply KCL at different nodes, you will be able to get this. In fact, you have to apply KCL at this node, let it be A, and you have to apply KCL at node this. Solve the circuit at these two nodes. You will be able to get the output impedance. Okay, so our objective is to calculate Zi equal to Vi upon Ii. Just use our knowledge, our understanding that these two input terminal voltage is same, these two input terminal voltage is same. So if I am writing Va here, there will be also Va, and there will be also same voltage, like that I can do. So by using that understanding, you can go for that. This time giving you 2 minutes time. Are you able to do this thing? So this is VA and this voltage is also VA, and KCL at node A, when you apply KCL at node A, you can say VI minus VO1 upon Z2. This is VO1, so this is VO1 and this is VO2. This is output voltage VO2 and this is output voltage VO1. So this VO1 and VO2, this is VO1, this is going from here to here, and this is VO2, this is going from here to here. So VI minus VO1 will upon Z2 plus VI minus VO2 upon Z3 equal to 0. At this point क्या किया मैंने, VI माइनस VO1 अपॉन Z2 ये करंट प्लस VI माइनस VO2 अपॉन Z3 इक्वल टू 0 कर दिया. ओके. अब सिमिलरली KCL एट नोड बी पे KCL लगाएंगे, क्या हो जाएगा, VI अपॉन Z5, ये यहाँ पे जो करंट जा रहा है, प्लस VI माइनस VO2, ये VO2 अपॉन Z4 इक्वल टू 0. सो VI अपॉन Z5 इक्वल टू VO2 अपॉन Z4 माइनस VI अपॉन Z4. थोड़ा सा फटाफट कैलकुलेशन कर लीजिए आप. इसके बाद थोड़ा सा कैलकुलेशन है. VO2 इक्वल टू लिख सकते हैं Z4, ये VO2 है ना, Z4 VI प्लस Z5 VI अपॉन Z5, और VO2 इक्वल टू Z4 प्लस Z5 अपॉन Z5 इंटू VI. ये हो गया हमारा इक्वेशन नंबर 2. सपोज ये था इक्वेशन नंबर 1 और ये इक्वेशन नंबर 2. अब इनपुट करंट कितना होगा, II इज इक्वल टू VI माइनस VO1 अपॉन Z1. या लिख सकते हैं VI माइनस VO1 अपॉन Z2 इंटू Z2 अपॉन Z1 लिख सकते हैं. ठीक है. तो इसको क्या लिख सकते हैं, VI माइनस VO1 अपॉन Z2 इज इक्वल टू II इंटू Z1 अपॉन Z2. इसको चेंज कर दिया. इसको लिया हमने इक्वेशन नंबर 3. सब्स्टिट्यूट 2 and 3 इन इक्वेशन 1. Substituting 2 and 3 in इक्वेशन 1. इक्वेशन 1 क्या था, ये है इक्वेशन 1, VI माइनस VO1 अपॉन Z2, VI माइनस VO2 अपॉन Z2. तो ये यहाँ पे VI माइनस VO1 अपॉन Z2 का वैल्यू यहाँ पे अवेलेबल है, इसको यहाँ पे सब्सटीट्यूट कर देते हैं और VO2 का वैल्यू ही सब्स्टिट्यूट कर देते हैं। आप इसको सब्स्टिट्यूट करोगे तो आपके पास आंसर आ जाएगा। फटाफट सब्स्टिट्यूट कीजिए, ये हो जाएगा आई आई इंटू Z1 अपॉन Z2 प्लस VI माइनस Z4 प्लस Z5 अपॉन Z5 इंटू VI डिवाइडेड बाई Z3 इक्वल टू 0। सो आई आई इंटू Z1 अपॉन Z2 प्लस VI 1 माइनस Z4 प्लस Z5 अपॉन Z5 डिवाइडेड बाई Z3, ये हो जाएगा इक्वल टू आई आई इंटू Z1 अपॉन Z2 प्लस VI Z5 यहाँ पे जाएगा, Z5 से Z5 कैंसिल हो जाएगा, तो ये हो जाएगा VI Z4, इसको अपन 1 कर सकते हैं, Z4 अपॉन Z5 इंटू 1 upon Z3. Therefore, I can say that this is equal to जीरो है ना, दिस इज इक्वल टू जीरो, सॉरी यहाँ इक्वल टू जीरो है, ये भी जीरो के इक्वल है, तो इसमें से कह सकते हैं कि आई आई Z1 अपॉन Z2 इज इक्वल टू VI माइनस VI Z4 अपॉन Z3 Z5, सिंपल। और इस तरीके से हमारा ये अगेन वैसा ही रिलेशन यहाँ पे मिल जा रहा है कि जो ZI जो आ रहा है VI अपॉन II, सो ZI इक्वल टू VI अपॉन II विच इज इक्वल टू Z1 Z3 Z5 डिवाइडेड बाय Z2 और Z4। Z4 है ना, Z4. So this is the input impedance. Where with negative feedback is there in these two, both of these two, both of the inputs are there as negative feedback. You see here this is negative terminal of the op-amp, and this negative terminal is connected to the output from this feedback. So there is negative feedback in this case. You can see here is negative feedback. This is negative feedback, and here also this negative terminal is connected with this. This is feedback impedance Z3. So because this is also, here is also a negative feedback. This is a nice question that we can apply virtual ground or not. You can apply virtual ground because here is negative feedback in both of the op-amp. So therefore we can apply this. And you can see this is the equivalent resistance. So minus should also come, I think. Minus should also come. Okay. Okay, so you all must have got this one, or minus is there or not? Because the answer that I have in that minus is not there, but I am getting minus. So minus will come or not? Minus is coming or not? I don't know where I got mistaken. Oh, this will be minus Z4. This will be minus Z4. Okay, so this Z5 minus Z4, so this will be minus. Yes, this should be minus, then this will be plus, this should be plus. So this is actually positive. Answer will be a positive answer. Okay, so how this input impedance, now this input impedance generalized input impedance, what what it means? If I want to get resistance as a input impedance, then what I will do, I will take one impedance, just all impedances as resistances. So if I want to simulate a resistance by this general impedance converter, then if I want to simulate a resistance of 10 kilo ohm, then what will I do? I will do simulate a resistor of 10 kilo ohm. I have shared one link in the Google Classroom related to the lab experiment that can be done for this generalized input impedance converter. You can simulate resistances, capacitances using OPAMP. So if I want to simulate, what I will do, I will do Zi. So I will take Z1 10K and Z3 10K, Z5 10K, and divided by Z2 10K and Z4 also 10K, all resistance of 10K. So these two will these all will cancel, and 10K ohm input impedance I will get, the equivalent impedance I will get. And if I want to simulate a suppose if I want to convert this Zi into a capacitance, then I will take what I need to do. If I want to convert into a capacitance, then you can take 10K, 10K. This is Z1 you can take 10K, Z3 you can take 10K, and Z2 you can take 10K, and Z4 you can take 10K, and this is Z3, this is Z4, and you can take a capacitance here instead of J omega C, J of XC. You can take XC capacitance, so it will work as a capacitor. So capacitance design is easier. If you want to design an inductor, in that case what could be taken, you have to take any value of the value of capacitance in the lower side, means this should be then 10K, then 10K, then 10K, and this will be 10K, and other will be in any capacitive, this one. So then this will cancel, and this will be equivalent will be a inductor. 1 upon capacitance capacitive, this will be equivalent to Zi will be an inductor. Inductive impedance. So in that way also you can simulate an inductor using the generalized impedance converter. Okay, for details you can visit this thing, this our Google Classroom, where I have shared this one. So time is over, and I am also just turning on your attendance for today. Attendance link is given in the description. Do not click till the time I will say OK. Wait, I am not I wait till the time I will say OK that you can update. So just wait. Okay, this question is added, and okay, attendance link is visible to you, and just you can now fill the attendance. Attendance is started. 5 minutes are there for attendance. Okay, and also class is over for this. You can replay this discussion again to understand the generalized impedance conversion. Impedance conversion means that you are able to convert resistance into means a circuit based on OPAMP into a capacitance into a resistance. Link is available in the description of this video. I will share in this class chat also. Okay, thank you all.